I'd like to thank the organizers for the invitation. So the title of my talk is on the randomized horn problem in the surface tension of hives, and this is joint work with Aalok Gangopadhyay. So I'll start with telling you about the randomized horn problem. We'll define a relation lambda plus mu goes to nu if there exist Hermitian matrices A, B with eigenvalues lambda, mu respectively, such that A plus B has eigenvalues nu. So Weil asked the question of determining necessary and sufficient conditions on lambda, mu, nu belonging to the cone of eigenvalues, where we take the eigenvalues in non-increasing order for the relation 1 to hold. So these are going to be all real because the matrices are Hermitian. So as conjectured by Horn and proved by Klyachko, Knutson and Tao, the set Horn lambda plus mu consisting of the set of all nu in the spectral cone such that lambda plus mu goes to nu of possible nu arising from a given choice of lambda and mu forms a polytope known as the Horn polytope. Given by the trace condition, the sum of the eigenvalues of the first matrix and the sum of the eigenvalues of the second matrix being equal to the sum of the eigenvalues of the third matrix, together with a recursively defined set of linear inequalities known as the Horn inequalities. So there is a natural probability measure on the Horn polytope. We'll denote it Horn lambda plus mu, referred to as the Horn probability measure, defined as the measure of eigenvalues of A plus B when A and B are chosen independently and uniformly from the space of Hermitian matrices with eigenvalues lambda and mu respectively. So this is supported on the Horn polytope. I'll tell you what a hive is now, because that's going to play a role in the sequel. So a hive is a...
Can I ask a question?
Yeah.
You have some intuition for how, for example, this is not the same as taking the eigenvalues and rotating the eigenspaces uniformly at random. This measure, is it?
You have to add the matrices and you get the spectrum. That's what it is.
No, I'm trying to understand what this measure looks like. So can I just take diagonal matrices with lambda and mu, just do higher unit independent higher?
Yes.
That is the same measure?
It's the same measure.
Okay,
yes.
Good.
Okay, so these hives are actually triangular arrays of numbers where certain rhombus inequalities are satisfied. So these rhombus inequalities have the following form. If you have a rhombus with entries A, B, C, D, then in this, the sum of the values on the shorter side has to be greater or equal to the sum of the values on the longer side. So what that means in practice is if you take so this is an example of a hive. If you take the piecewise linear extension of the numbers written here on the small triangles and view it as a surface in R3, so it's a concave surface. So that's what it means if you take piecewise linear extension. And the eigenvalues come on the boundary. So if you take lambda equal to 40, 30, 20, 10, mu equal to 40, 30, 20, 10, and nu equal to 65, 55, 45, 35, what you do is you write the eigenvalues on the boundary as the differences, successive differences along these sides. So this gap is 40, this gap is 30, this gap is 20, this gap is 10 because it's determined by lambda. Then you go down here and you're determined by mu. So you add 40, add 30, add 20, add 10. So that is for mu, I'm sorry. And then to encode nu over here, you write 0, 65, and you add 55, add 45, add 35. And of course, if the trace inequalities don't work out, then you're not going to get the same thing when you go up and down like this and when you go sideways. So you won't have a consistent system. So this only works when the equality of the sum of the traces of the first two matrices is equal to the trace of the second. So now what you have to do is you have to write numbers in the interior in such a way that all the rhombus inequalities are satisfied. Namely, this plus this has to be greater or equal to this plus this. So when you write 125, 100, 150, for example, when you look at this rhombus, you see that 125 plus 120 is less or equal to 100 plus 150. And this has to be true for every rhombus. So if this is true, then we say it's a hive. So are there any questions about the definition of a hive?
So the boundary data is fixed.
The boundary data is fixed. So what Knutson and Tao showed was that you have there exist triples of matrices x, y, and z such that x plus y is equal to z with respect to spectra lambda, mu, and nu, if and only if a combinatorial structure of this form exists. So it's this polytope is a certificate. The points in this polytope are certificates for whether you have matrices with these properties. But we are interested in a question related to a measure on this polytope, namely the Horn measure. So this Horn measure is a measure which is a piecewise polynomial. It was computed explicitly by Cucurella and Zubair. It's given by this formula. These are van der Monde determinants. So nu, lambda and mu correspond to the eigenvalues lambda, mu. Nu is for, of course, nu. This tau is one fixed vector. It's always n minus 1 all the way up till 1. So it's just a constant gap vector. And this is the volume of the hive polytope when you put the entries lambda, mu, and nu on the sides. So this is the probability density of observing nu when you add two random matrices with eigenvalues lambda and mu. So it gives you an exact characterization of what the probability density is when you add two random matrices spectra lambda and mu and look at its spectrum.
But what's tau? Oh, okay.
So tau is this vector. It's fixed gap. So n minus 1 all the way up till 1. So yeah, so the GUE matrices that we'll be looking at will be normalized so that the diagonals are all normal 0, 1 real Gaussians independent, and the non-diagonals are complex normal 0, 1 with the Hermitian condition enforced, and otherwise you have complete independence. So this is the first theorem I'd like to discuss. What it says is that if you take the subspace defined by the set of this constraint, the traces adding up, then and you look at a certain log concave measure which is defined in this way. So I'll break this down for you. So these are just those van der Monde factors. This is the volume of the Horn polytope with boundary lambda, mu, and nu, and this is a Gaussian that we are multiplying by it. So the idea is that you have some sort of log concave measure on this cone of triples of spectra, which add up in this nice way. The traces add up. And from that, we're going to get some information about the quantity hn, lambda, mu, nu. Okay, so what this is saying is that if you take this function, which encodes the volumes of hive polytopes and some other van der Monde factors and this Gaussian, you integrate it over the entire subspace, you get a closed form. You get 2 pi raised to n a square b square c square by a square plus b square plus c square by n square by and raised to n square by 2.
Does lab mean Lebesgue measure?
Yeah. So the proof is just by using this formula of Cucurella and Zubair and taking two GUEs with variance a and b, adding them, and basically doing the convolution and measuring what you get when you add two GUEs. And of course, if you add two independent GUEs, as we are doing, you get another GUE whose variance is the sum of the squares, sum of the variances of the individual GUEs you started off with. So we start with one GUE here with standard deviation A, and we take another, and this is the formula which tells us what the spectrum of nu is, what the density of at nu is when you add two random matrices with spectra lambda and mu. So if you just take the product of this, these are some normalization factors associated with the GUE, call that C tilde, then double integral over Rn and Rn of C tilde f is equal to this quantity. It's the product of GUEs, it's that other factor with the exponential thing for the C square. So for the A square and B square, it got contained in the fact that we are taking the GUE measures in the beginning, but this C square we have to put in extra. And then you note that the sum of two GUEs of the kind we took has this measure. You have to account for this multiplicative factor as well. But when you multiply a GUE with this factor, you can, using completing the squares, you can absorb this into the GUE with some factor out that pops out. And this is the GUE that you get. But of course, a GUE measure is a probability measure. It integrates to 1. So when you integrate once more over Rn, you get just this. So that's why this triple integral just integrates out to this, and there was that C tilde factor that encoded the A's and C's. So this is why what you get this factor. So this is the proof of this closed form.
This Hn is the volume of that polytope?
Yes. For different lambda, mu, and yeah. But lambda, mu, and nu are varying. Yeah. So actually these van der Monde factors are nicely encoded as the volumes of Gelfand-Setlin polytopes, which I'll describe now. So these Gelfand-Setlin patterns are can be thought of as the discrete x direction derivative of a hive. So this is I mean, in a sense they are simpler than hives, but that's the relation to hives. So this is always greater or equal to this, and this is always greater or equal to this. So this is true for any triple of this form. This greater or equal to this, greater or equal to this. And what's the relation of this to the hive inequalities? It's just that if you took this hive inequality, rhombus here, and you wanted to encode the rhombus inequality, it's precisely this greater or equal to this. So that's why these interlacing constraints are related to hives. But there are also in the hives these additional vertical rhombi which are not figuring in this picture because you're only looking at the x derivative. So you have this interlacing condition. And so what we want to do is we want to interpret that previous integral as the integral of a simple Gaussian, a plane Gaussian, over some other higher dimensional Euclidean space. That higher dimensional Euclidean space happens to be a different cone of dimension roughly 2n squared. Recall that the previous cone had dimension 3n minus 1. Now the cone has dimension roughly 2n squared. What it consists of is, it consists of a hive, and then on the sides you have to paste Gelfand-Setlin patterns, 3 Gelfand-Setlin patterns. So this is a hive, and these are all Gelfand-Setlin patterns. So recall that the slopes here were lambda, mu, and nu. So you paste the Gelfand-Setlin pattern with eigenvalues lambda, mu, and nu on these sides. So this is what I'm going to call a triply augmented hive. So the point is that the volumes of these Gelfand-Setlin polytopes are known to be v lambda by v tau exactly. So instead of having a multiplicative term of the form v lambda v tau, what you can instead do is you can look at the space of such gadgets. They form a 2n squared dimensional cone, and you can integrate. So this just encodes those multiplicative factors just by the volume of the space, and then you have just a plain Gaussian. So that integral is the same as just integrating a Gaussian over the cone of all possible such patterns. So once you do that, there's basically a theorem of Boltzmann which tells you that the maximum entropy measure when you fix the variances of the 3 sides, that is the total L2 norm squared of the 3 sides, is maximized when you pick a Gaussian. So on this cone. So this measure that I just spoke about is therefore the maximum entropy measure on this cone, and that gives us some handle on the hive volumes. So just by some calculus involving or some algebra involving the GUE, you can say that the expectation of nu squared, let's say this is the expectation of the norm nu squared is this, and similarly for the other two, it's the same sort of expression with some cyclic permutations. So this basically the theorem of Boltzmann, which boils down to some Kullback-Leibler divergence computations, tells you that if you look at the maximum entropy measure that satisfies these three expectations constraints, it is precisely this Gaussian. This is the one that we're looking at. It's proportional to this quantity on this cone of dimension roughly 2n squared. So, but that is now useful for us because we can derive from that some control over these quantities. So what it follows from that, if instead of looking at this Gaussian measure on the cone, you just sort of essentially fixed the three sides and looked at the uniform measure up to that. You can't exactly fix it because then the differential entropy will go to, well, it'll not be finite, but you can give it very little leeway, like in smaller than inverse polynomial even, and then you can basically talk about the same object, and what you get is that the entropy of such patterns, when you fix the boundary to any lambda mu nu that satisfies these conditions, will be less or equal to this maximum entropy measures entropy. So this gives you some control over this for any lambda mu nu that satisfy these constraints. And secondly, because the GUE eigenvalues concentrated around the semicircle, when you look at the histograms, it tells you that if you were specifically to choose lambda mu and nu from the GUE eigenvalue expectations of the GUE matrix eigenvalues, then you in fact do achieve this up to little o1. So this entropy is actually achieved up to little o1. So to do this, you have to use the fact that this measure is log concave, and you have to use some facts from the geometry of log concave functions. So basically, we use this theorem of Fradolisi, which says that if you have a log concave function and you evaluate log concave density and you evaluate it at the mean, then the value is no smaller than e to the minus dimension times the value at the mode. So this is a very nice theorem of Fradolisi which we use. So you can basically restrict to the mean and guarantee that the entropy will be pretty close to what it can maximally be. So now I'll talk a little bit about exactly sampling random augmented hives, because this is going to be useful in some of the computational experiments we did.
So the conceptual point of that theorem, do you get an upper bound on these volumes of these volumes?
Yeah, you do get, yeah. So we get upper bound, and it's a tight upper bound, this is it's kind of achieved. Yeah. So if you take a random Hermitian matrix with given spectra and you look at the minor process, then you get a random Gelfand-Sittlin pattern. And it's a result of Baryshnikov that this is actually a uniformly random Gelfand-Sittlin pattern from the polytope of all possible Gelfand-Sittlin patterns. So sampling from this polytope is equivalent to picking a random matrix and looking at the minor process of that random matrix. So what we want to do is we want to pick a random Gelfand-Sittlin pattern and turn it into a hive by using large gaps. So this is a Gelfand-Sittlin pattern. What we are going to do is we have turned it to its side, and then we are putting large gaps here, lambda 1, lambda 2, lambda 3. Okay, so these are so big that when I enforce these differences here, I'm guaranteed to get a hive from that Gelfand-Sittlin pattern. So basically, we are embedding a Gelfand-Sittlin pattern in Gelfand-Sittlin polytope inside a hive polytope by giving it sufficiently enough leeway here. And conversely, every such hive with this large gaps here will indeed correspond to a Gelfand-Sittlin pattern if you just look at the x derivatives here.
So large gaps means.
Large gaps means, I think it's there next. Yeah. So large gaps means that the successive gaps have to be large compared to the maximum discrepancy between the eigenvalues of lambda. So it's been greater than. This is what we mean by large gaps. So really large gaps, but that doesn't affect us. So this is how we can construct a hive from a Gelfand-Sittlin pattern, and here is the values of the hive. So what we'll be doing is we'll be taking double hives. So these double hives are basically two hives pasted together, but the rhombus inequalities don't need to be satisfied on the rhombi that straddle the equator. All other rhombuses have to be satisfying the rhombus inequalities, but the ones that straddle the equator, they don't have to satisfy the rhombus inequality. That's what we call a double hive. It's basically just two hives pasted together which agree on the boundary. So we're going to take a random matrix X, get a random Gelfand-Sutton pattern, and turn it into a hive using large gaps. Take a random matrix Y, get a random Gelfand-Sutton pattern, turn it into a hive using the same large gaps. You can't independently choose the large gaps because once you choose lambda, it essentially fixes the large gaps everywhere because that's the degree of freedom in the system. Okay, so we're going to construct a double hive using this probabilistic process. And then we're going to apply something called the octahedron recurrence to this pair of hives. So this was introduced in I don't know when it was introduced, but in this context of hives, it was used by Knutson, Tao, and Woodward. Okay, so we're going to run this octahedron recurrence over a tetrahedron. The top two panels will contain the double hive, one hive on each of the top two triangles. So one hive on this triangle, one hive on this triangle, and then we're going to run a process on this. So this is the process. What you do is for all the lattice points inside this tetrahedron, you require that this relation holds. So F plus E has to be equal to the max of B plus D and A plus C. Okay, so this is the octahedron recurrence. So if you have the top 5 values, the last value F gets determined by the top 5 values. So we're going to run this recurrence, and then you're going to get something on the bottom 2 panels. And what you get on the bottom 2 panels will be an augmented hive. Namely, it will be a random hive with the right boundary here and here. Here you're going to get some Gelfand-Sutton pattern, which is also what we need from the Horn, from the inequality of Curio and Zubair. And here we have a hive. Okay, so this is what it looks like. So you run this octahedron recurrence and you get this. So this relation of which was sort of in an implicit form or a less explicit form mentioned by Knutson and Tao, and in a more explicit form mentioned by Curio and Zubair, you notice that you have a V gamma factor over here. And as I mentioned, V gamma by V tau is precisely the volume of Gelfand-Sutton patterns with gamma on one side. So this whole thing, this V mu and V nu are fixed in this picture. So they don't really play a role, they're just constants. So this whole picture is precisely the volume of this augmented hive polytope, where you have a hive with fixed boundary here and here. This is free, but there's a Gelfand-Sutton pattern pasted to it, and then you're allowing that to vary freely. So this pattern, which we call an augmented hive, has basically this as the volume. So one way of generating a sample from a distribution from the Horn probability measure is to do the following. Pick a random point from this augmented hive polytope and simply measure what you see on this middle side. And if you look at the slopes of the lines on this, you will exactly get the right measure. It's the probability measure of the spectrum of the sum of 2 random Hermitian matrices with the right spectra. So this is so in this form, I think it was used in work with Sheffield and Tao in 2024, but it was based on this work of Knutson Tao Woodward from 2004. So this is the process now. We are interested in GUE hives, so we're going to sample GUE matrices, take the minor process, construct a double hive, run the octahedron recurrence, and obtain this GUE hive from that. And we want to study the shape of this thing. So I have a Yeah, so this is what you get if you take 1,000 samples of n equal to 250. So this is what a hive looks like. Uh, so one can see that the third side is a bit is an arch that has a higher that is taller than the other two, and this is simply because the GUE that it is a variance 2 GUE, whereas the sides we started it with were variance 1 GUE. So this is just like the standard deviation has increased when you added. So that's why you see this bigger thing on the third side. So this is the general form of a GUE hive that we're looking at. I have sigma x on one side, sigma y on one side, and sigma z equal to square root of sigma x squared plus sigma y squared. So what we want to do is we construct some sort of canonical hive first, a GUE hive, and we'll compare the limit shapes that we seem to get with this canonical shape. So this is what you get when you set one of these sigma y's to 0. So when you set it to 0, it's basically flat. So you get some kind of foil-like, aerofoil-like shape. And this is what you get when you have 1, 0, 1. Now if you take 3 of these, and you take convex combinations of these with the right proportions, you will get a hive with the right boundary conditions.
I'm a little confused what you're plotting here. I mean, so you constructed this hive, it's this discrete, right?
Yeah.
The numbers living on these
Yeah.
on these triangular points, right?
Yeah.
And then what did you do? Like, it's random? So you drew it at random from the set of all hives associated to these spectra?
Yeah.
But why does it look so smooth?
So this is for 250 or something. So it's very large n, so it's smooth.
So are you claiming that it self-averages? Like in the limit it becomes deterministic? Does the variance go to 0 of these?
So that is a theorem that I have with Knutson, with Tao and Sheffield.
Okay, so you get a deterministic limit shape, and that's what you're plotting.
So what was proved in that paper was that the variance tends to 0, and that the expectation also converges to a limit when suitably normalized is a result that I later proved recently. That's also.
Okay, and so that's what we should be thinking when
Yeah.
we see these plots. Though
Yeah.
that's kind of the limit shape of these.
Yeah. Yeah, but the reason I'm doing this is I want to get a handle on the surface tension, which I'll introduce soon. Okay. So this is now a way of producing what I'm going to call a continuum hive. So these are now functions on the continuous triangle. I'm going to take these 3 surfaces that you get by taking on these on lines parallel to this line. They're going to just be straight. So it's basically a one-dimensional thing that is governed by the GUE eigenvalues. So this is what you get when you set one of the variances to 0. It is essentially a unique hive that satisfies this condition, the hive condition. It's a point. The hive polytope degenerates to a point when one of the spectra becomes 0, and you get one of these. And then we're going to take these convex combinations of these to just produce some canonical shape. So it turns out that this is not actually the right limit shape, which we can actually prove. But as a heuristic, it seems like a good approximation. Okay, so it's just a convex combination. We're going to take these convex combinations of these shapes. And what we did here was we took the average of lots of sampled GUE hives. So this is the real limit shape, if you will. This is that hypothesis that you get by convex combinations of those things. And this is at a scale of roughly 6,000. So these heights are 6,000 or so. And the gap, the difference between these two is of the order of 200. So it's less than a 4% difference between this and this when you take sigma x, sigma y, sigma z to be 3, 4, and 5. So they seem quite close, but this is just a heuristic. But we're going to use this in some computations later. So now I'll introduce this surface tension. So associated with a hive, which is this concave surface, we're going to have 3 parameters, namely the average slacks on the rhombi of the three types. So we're going to call that S0, S1, and S2. So you should think of these as some sort of mixed second derivatives of the surface. And the mixed secondary, the discrete version is this, precisely this. It's the hive slack. So what is the surface tension? So the surface tension is essentially what you would see if you took an enormous hive with periodic Hessian of a certain average Hessian. So you enforce only that the Hessian is periodic and that it has an average that is S0, S1, S2 in these three directions, if you will, these three in these three mixed derivatives. So what you do is you get a polytope out of these periodic hives. So you can think of them as living on a torus up to. Yeah.
What are the boundary conditions as n goes to infinity on these?
On this?
Yeah.
So this has to be equal to this, let's say. But then I can't talk about hives. I have to add to this hive, which is a concave surface, a convex surface, which is of the right quadratic, which is a quadratic, and then you will get that these boundaries exactly match. Because if you take a concave function with a periodic Hessian, one way of making it a bounded function is to add a certain convex quadratic, and then it will become a bounded function. So we are doing that, and if you do that, then you're not looking at concave functions on this lattice anymore. You're looking at semi-concave functions on the lattice because you've added a fixed convex function to it. So it's a polytope in any case, based on some constraints. And we are essentially looking at the limit as n tends to infinity of the volume of this polytope normalized by raising it to 1 by the dimension. So firstly, one can show using Brun-Minkowski that sigma of s is convex. The negative log is convex. Secondly, one can show that it is symmetric in S0, S1, and S2 by the fact that although in this picture the torus is drawn in this way, there is a way of deforming this torus while not really changing the picture, where you shear this triangle and place it down here like this, and you get this parallelogram, and that's also actually exactly the same thing. So it's S0, S1, and S2 is the same as when you permute the S0, S1, and S2. And what is known through the work of Knutson and Tao and Johnston is that this volume, when S2 tends to infinity, has a nice closed form, which comes as the surface tension of Gelfand-Zetlin patterns. So this is known.
That sounds fucking awful.
So this log of V of, so I'm looking at the classical eigenvalues of a GUE now, and defining basically the analog of this Van der Monde determinant with a logarithm and normalized, and that's going to be V of lambda CL. And this is an identity that is, I guess, related to some of the things that we saw already. It's equal to 5 by 4. So repeating what Knutson, Tao, and Creux-Zuber have said in explicit forms due to Creux and Zuber. So we introduced with Sheffield this surface tension for hives. So this is the surface tension of for the problem of finding large deviations for the spectrum of the sum of two random Hermitian matrices. So if you take two random Hermitian matrices with spectra lambda and mu, add them independently, and look at the spectrum of the sum, the probability that it lies within a certain ball of nu n is, when suitably normalized, has this large deviation form. It's the infimum over all hives of the surface tension of all hives which have the right boundary conditions. So somehow the best hive is the one that minimizes the surface tension, and that's the one that tells you how you're going to get nu n from this lambda n and nu n. So this is, I guess, more or less repeating something that I said before. It's saying that when you take the classical eigenvalues, you get the same thing. Earlier I said it for the expected eigenvalues, but the expected eigenvalues and the classical eigenvalues are known to be extremely close. So you can replace one by the other. But there's this smoothing factor here. But this is essentially saying that this hive polytope volume is given by this when you normalize it. That's what this is saying, because these two essentially cancel out. So now if you translate it into the surface tension statement, what this is saying is that if you fix the boundaries of this continuum hive to lambda mu and nu, and you take the infimum over all hives of the surface tension integral, that is exactly this. Okay, so we don't know the shape of this hive, but we do know what its total entropy is somehow when you normalize it properly. And now we're going to try to do some numerical computations with them. So what we're going to do is we're going to discretize and write that integral as a sum over the surface tensions. And we know the value from the right-hand side of the previous equality. And we're essentially going to solve a bunch of linear equations with the constraint that sigma, we're trying to find sigma. We're going to find sigma when S0 plus S1 plus S2 is equal to 1, because when S0 plus S1 plus S2 is not equal to 1, there's a simple scaling that allows you to go back to this case. If we want to find sigma, what we're going to do is we're going to discretize, write a bunch of linear equations, and additionally enforce the constraint that sigma is convex. So this is apparently helpful, because when you have a constraint problem, you want to you get better answers. So we're going to constrain it to being convex, and this is how you get back to S0, S1, S2 adding up to 1. It's just that the scaling relation is always going to be true. So there are some details about looking at barycentric coordinates and doing the discretization properly, which I think I'll skim over. And but the point is that it's not enough to know the total entropy of the hive or the surface tension integral. You need to know the shape, because if you don't know the shape, how are you going to write the equations, right? But we don't know the shape, but instead we're going to use this surrogate, which is this hypothesis that we have, which we know is not generally true, but it seems to be a reasonable thing in practice. So we're going to take these, assume that the shapes are actually given by these convex combinations of these elementary hive shapes, continuum hive shapes, and get a bunch of linear equations. So we get a bunch of linear equations where the right-hand side is given by that equality that we saw in the beginning with some minus 5 by 4 and some other terms. Then when we solve it, we get a numerical expression for the surface tension. So this is purely numerical. It's just, I've taken e raised to minus sigma num, and this is what we see when you, on the triangle S0 plus S1 plus S2 equal to 1. But I mean, once you have this formula, you can try to fit some functions to it. And we found that this particular function, which is certainly not exactly the answer because it doesn't match the boundary conditions of Aalok and Tao and Johnston, but it seems like a good approximation in many situations. Like the 0.71171 for these values, here it is, the numerical thing is 0.172, and here it worsens, but it seems like a reasonably good fit. And the actual numerical thing that we computed actually does match the boundary conditions of Aalok, Tao, and Johnston. This is empirically true, that the limits do match. Now I want to get some bounds in the surface tension using the results we have derived. So this recall that this was one of the inequalities that's true for any lambda mu nu that have these norm bounds. And this is the surface, this is this large deviation principle for hives. So we are going to apply it. Note that this is an infimum over all hives with these boundary conditions. But this infimum is therefore a lower bound on any specific hive that matches these boundary conditions.
I'm
So
confused what is going on here. Can
Yeah.
you explain? So what is BIN?
So this is a topology. So it's a ball around v nu n of radius epsilon. I haven't told you what kind of a ball it is.
What is mu n?
Nu n is a spectrum. It's a set of eigenvalues. So
Any sequence nu n, but there's no nu n on the, there's only a nu. So what is nu on the right-hand side?
Or is it?
yeah, so the un is the natural discretization of nu. So nu is some curve.
Nu is a continuous curve.
Yeah.
And then what is nu n?
Nu n is what you do when you just say, take the natural discretization of it at equal intervals.
Okay. At integral, okay, yes. It's a curve from where to, I don't.
So there are two things here. Here is a spectral thing. Nu is somehow the continuous version of a set of eigenvalues, and it is viewed as the left derivative of gamma prime, which is to be viewed as the hive boundary, because the left derivative of the hive boundary is what gives the spectrum.
So you take nu as a curve, let's say from 0, 1 to R?
Yeah,
Okay.
non-increasing.
Just discretize this as a, let's say, n points.
Yeah.
Right? Just uniformly.
Yeah,
And that's nu n.
yeah.
I see. So this is, you're looking at a ball around a point that has a set of eigenvalues that has a limit shape. You specify the limit shape, you want
Yeah.
to know, I see.
So technically, the way the discretization is done is the following. You look at this continuous boundary of the hive, and then you take these intervals, and the slopes that you get, these are the lambda I. I mean, these are the nu n. So this is nu n of 1, this is nu n of 2, and so on. But so it's not exactly, it's like this. Yeah. So what you get by just putting a quadratic hive in that continuum hive in that situation is you get an upper bound on e raised to minus the surface tension of this form. And then some similar arguments also give lower bounds, but this is now up to a factor that we don't have good control over. So you get a lower bound of this form using convexity of the surface tension and a kind of Green's function. So these Green's theorem. So basically these canonical hives that we defined, you know what their total Hessian is because they are so explicit, and you can use that that bound to get this basically. So here's some numeric. So this the lower bound is roughly 3.5 here, and the upper bound that we just got earlier is roughly 4.1. So it's not too far. But the lower bound has this inexplicit term, which is basically the gap between our canonical hive and the true limit shape, which we don't know actually. But just going by the sampling results, they seem very close. But that's something we don't have good control over. And this actually shows that gamma is not always 0. So this we can prove that because basically this limiting behavior at the boundary is known, and that 4e by pi doesn't match up if you substitute. So now I'll quickly go through some things on lozenge styling. So how much time do I have? Okay, so I'll just go through this very fast. Or is that fine? Yeah. So this is, so this octahedron recurrence seems somewhat opaque, but it has a closed form expression using something called Spear's theorem. So it's the value that you get at the bottom hive on the augmented hive is equal to the weight of a maximum weight matching on a certain octahedron, on a certain excavation hexagon in the upper two panels. So I'm going through this very fast, but it's basically something explicit. So you can get control over the value of a random hive. It's, however, the total weight of a maximum weight matching in some random environment. So it's not a very simple object, but one still gets control over it. And this is what those hives, those maximum weight matchings look like when you replace them with lozenge tiling. So in the large. So we expect that this would also have a limit shape, but we are nowhere near proving something like that. So these are 4 excavation hexagons, and correspondingly the maximum weight matchings that you get. So some related research on Gelfand certain patterns is this result that I have reported that talked about many times. Schlatt and Tao with the appendix by Jekyll have shown that the limit shape of a Gelfand certain pattern on large N is characterized by the minimizer of an integral of this surface tension. And Johnston and Prochnow recently proved a large deviation principle for these patterns with the same surface tension. And on hives, by analyzing these lozenge tilings, it was shown in work with Scott Sheffield and Terence Tao that the variance of the augmented hives, GUE hives, tend to 0 if they are normalized to have an expectation that is bounded above by a universal constant as n tends to infinity. And building on this, we recently showed that not only does the variance, the variance was shown in the previous paper, and this paper we show that the expectation also converges as n tends to infinity to a single continuum hive. So here are some open problems. Is there a closed form analytic expression for the surface tension of a hive as a function of S? Is there an asymptotic shape for tiling height functions? Now, are there analogous sets of results for integer valued hives giving asymptotics and bounds for little digits and coefficients? So, thank you very much.